Hi, my name is Ibrahim Dawod, and I'm a joint PhD student between SPB SFX at the European XFEL and the Chemical and Biomolecular Physics group at Uppsala University in Sweden. My research relates to imaging of biomolecules using X-ray photon lasers. And specifically, we try using theory to understand processes which can limit the obtainable resolutions in bioimaging with XFELs. And this can be, for example, studying photon-matter interactions, so looking at what happens to the sample when it's exposed to high-intensity X-ray pulses. And the reason that we're doing this is because we want to understand the structure of a biomolecule since it relates to their function. Our theoretical simulations are useful for the community, for example, designing future experiments. For instance, guiding the choice of particular experimental parameters that could be used so people can acquire the best possible outcome of an experiment. In my current project, we've partly used SimEx, a software suite used to simulate experiments at light sources, and also Gromacs, a classical and molecular dynamics simulation software. And we wanted to use more realistic pulses as produced from SimEx as an input to Gromacs' radiation damage calculator. And this required some software development from us, where we needed to make Gromacs be able to read the input from SimEx and afterwards make the output of Gromacs readable to SimEx such that we could use the rest of SimEx's software pipeline. Here I have a demonstration of part of my work where we've combined SimEx with a software that we currently are using in Uppsala University called Gromacs. And I'll start this demo by speaking about a big part of this project where we've taken pulses, so SASE pulses, which have been propagated through the optics of European XFEL, which gives sort of realistic shapes of the pulse. And if I run this block, we will see an example of how each pulse that a sample will interact with, how different it will be for each time, for each shot. So if you look at the different colors, each color corresponds to a different pulse. And this gives you an indication of how varied a single experiment can be. Then we've taken these pulses and inputted into Gromacs. For this demonstration, I have prepared a molecule called ubiquitin. And before you can run the photon-matter interactor, you need to do certain steps, like minimize the energy of the system and potentially run some molecular dynamic simulations if you want the system to acquire certain properties, such as temperature and pressure. And here we've prepared a molecule where we've minimized the energy such that we get a realistic system. Then, after we've created the molecule, which I've already done, we run this photon-matter interactor block. And here we've have certain parameters that we can choose from. For example, currently we've implemented only that you can input temperature, so you can use, here we have used 300 Kelvin, and then we input the previous molecule, so the prepared one, which we've minimized the energy. And this interactor here has a lot of stuff behind the scenes, where the most important part, the new thing about this is that we've taken the SASE inputs and made it so that Gromacs can read them. And now this block here takes a while, so I've already run this. But the output here, we can look at how each pulse affects the resulting damage in the molecule. So I've plotted here on the x-axis the time, and y-axis the number of ionizations, sort of to give an indication of how much damage we have in the molecule. And as you can see, each color here corresponds to a certain pulse. And we have a spread in the number of ionizations as a function of time, which gives an indication of the importance of using different pulses for each shot. Then we have the imaging part. So we want to calculate some diffraction patterns. And then for this, we need to set up a detector. So for example, the number of pixels, the size of the pixels, and distance from the sample to detector. So these are the most currently the most important parameters. And also you can choose certain things, as if you want to rotate the sample, and for example, inelastic scattering, for example, but we have not currently implemented this in this version. Finally, you can run this interactor here, which I've already done also. And then we come to the analysis part. So we can run this block to get a visualization of this diffraction pattern of our molecule that we had in the beginning. And of course, different pulses will give you different damage pathways, as we saw before. And this will result in that the diffraction pattern also can differ for each shot. So finally, we have some references where the base for this work, the two papers on Gromacs, and also the two papers which SimEx is explained. So the next steps for us with this project is to see if we can further improve the modeling that is used in Gromacs for calculating damage, and also implement, for example, calculations of form factors so that we can calculate inelastic scattering, for example. And further, we might look into larger systems, so perhaps larger proteins or even potentially viruses. Thanks for listening to this interview and demonstration. And if you like to get in contact with me, you can email me.